Now, see, that's what I'm trying to
Now
quell the
that you
storm.
said we're gonna lose,
I'm like an old woman.
Okay, here we go. All right. Now I have another interesting thing to teach you here. If you add, okay, so if you have two solutions, write this down, please. So you have solution A and solution B, and you mix them together to make an overall solution C. Okay? Let's say this is a solution and it's 150 milliliters, and this is a solution, it's 150 milliliters. What is the volume if you mix them? So if you mix, so A and B are both mixed in C, it's not a trick.
How many what?
So 150 in A, 150 in B, you mix those solutions, you pour them completely, empty A and B completely into C, mix it up.
Yeah.
What do you think the total volume will be? 300, right? Okay. 300 milliliters. Okay. Good. No. In real life, that's not actually how it's going to work. On paper, we assume that. All right? The way we word it, how do I word it here? Assume the mixtures, or assume the solutions are, the volumes are added. That's what it says. It says assume volumes are additive. What does that mean? Assume 150 plus 150 is 300. But in real life, when you mix solutions, often the volume decreases.
Because some go poop.
What happens?
Bye-bye.
No, they don't evaporate.
because like some of it's still not going to Texas.
What would cause the volume to decrease? Volume is the amount of space something takes up.
They're reacting with each other.
You're getting closer.
It's creating something that is less.
How?
They combine it with making like a make them smaller.
Say it again.
They're making like a precipitate.
No, no precipitate. They dissolve completely. All right. So, if you guys were gas particles, right now you're taking up a certain amount of space, right? How could you take up less space if you were gas particles?
Get closer.
Ah. Why would particles get closer?
Because they're trapped in.
That's the answer. So in real life, sometimes when you mix solutions, volumes will decrease because the two solutions might be attracted to each other. And the particles in here, when they become attracted to each other, move a little bit closer, so it actually decreases their volume. I've seen this mixing things, and it's kind of crazy. Sometimes it is noticeable, sometimes it's very small. Obviously, on paper and on problems that we need to know volumes, you don't know. You have no idea what the volume is actually going to be, so you just assume it's 300. So yes, it is 300, but I'm just using that to kind of teach the concept here. All right, that's something I never really. I don't remember if I was taught or not, but I didn't really get that until I started teaching AP Chem, and it made complete sense once I started teaching it. But it's pretty cool because you can witness it with some solutions. Like dissolves like, that kind of stuff. It depends on the forces of attraction. How close those particles get. All right, so I want to give you one sample problem here, and then we will start talking about gases, and then we will call it a day. All right, here we go. So we have two solutions here. Let's use this example here. I'm just gonna relabel these. I should have just used this example the first time. Let's say we have solution A, which is 1.45 moles per liter of KNO3, and in that beaker we have 55.3 milliliters. In beaker B, we have same thing, KNO3, but it's 0.75 moles per liter of KNO3. Sorry, 0.755. 0.755. And the volume is 22.8, sorry. 22.8 milliliters. All right. If these two solutions are mixed, calculate the final molarity. So what is the molarity of the final solution. And we assume the volume is additive. Again, so 55.3 and 22.8, we're assuming they combine completely, ignoring the forces of attraction that could screw it up. Okay. I'll give you one piece of advice, then I'll give you time. What do we seem to always have to find with a lot of these problems? Moles. That's the key. If you know the moles in here, you know the moles in here, and you are adding them in here, then you know the moles in here. And if you know the moles and you know the volume, you can get the molarity. So go ahead. I'll write down the other problems. You got those 5 problems due tomorrow. You got lab stuff you can work on too. Skylar, when are you taking that quiz?
Wednesday, and then I think you said the empirical Thursday.
Okay. You get answers yet?
Yeah.
Okay. So if we take 1.45, right? This is molarity is moles per 1 liter, and we multiply it by 0.0553 liters, right? Because that's 55.3 milliliters in liters, 3 decimal places. Liters cancel, you get moles. So for A, I get 0.0802 moles. For this one, I do the exact same thing, 0.755 moles over 1 liter times 0.0228 liters. Liters cancel. For B, I get 0.0172 moles. Questions on that? You guys good?
Mm-hmm.
Okay. So now you just add them together. So for molarity of C, 0.0802 plus 0.0172 divided by the total volume, so 0.0553 plus 0.0553 plus 0.0228. There's your liters, there's your moles. So that's moles over liters. So your molarity is 1.25. Oops. So essentially, the concept here is you have all the particles, all the moles from A and all the moles of B floating around, and then you add the two volumes. So you have to add the two moles, add the two volumes. Moles over liters gives you concentration. That's molarity. Questions? Okay, so those 5 problems are very similar to these. The one we did in the back, this one, and then the other one in the notes. All right, we still got a couple minutes. We're gonna use it. All right, let's talk about gases. I was looking for problem set 2. I can't find it. Don't worry, I will.
Is that 131, 181, 161?
Chapter 4, 84, 131, 76, 78, 160. All right, and probably have a quiz on this stuff.
No.
You'll have a quiz on this solution, stoichiometry, dilutions, precipitate problems. I don't know when, maybe next week. All right. Okay, gases, kind of a big unit here. A lot to learn. What do we already know? Let's talk about what we already know about gases. Anything you remember from last year? Anything else?
They move in random, straight.
Yes, they move in random straight lines. Good. What about forces of attraction? Weak. Good. Okay, what else? Anything else? They fill their containers. Good. What causes gas pressure? Gas particles colliding or bouncing off with each other in the walls of their container. Good. You guys remember any of the conditions that we talked about last year that affected gases?
High temperature.
Remember STP? What are those values? Do you remember? Standard temp is 0 Celsius, 273 K. Standard pressure, 101.3 kPa, 1 ATM. Good. Now in AP Chem, there's another set of conditions called normal. So there's standard and there's normal. I just find that funny.
Aren't those the same thing though?
No. Normal is 25 degrees Celsius. Standard is 0. No one exists in 0 degrees Celsius. 25 is more like this room. This room is probably like 20 degrees Celsius. So 25 is closer. It's closer. You guys remember, and we'll I guess end with this. Do you remember the 3 graphs?
Yes.
Let's start with that.
Pressure, temperature.
Let's just sketch them here. There's a 4th one we're gonna add. Let's do temperature and pressure. Let's do temperature and volume, and we'll do
Pressure one.
yeah, volume on the X, I suppose. Volume and pressure.
Can you write the thing on the board for PTV?
Oh yeah. So PTV, but now there's another symbol.
Okay, well, we don't care about that one right now.
All right, temperature. So remember, if we're looking at temperature and pressure, what's held constant? If the graph is showing temperature and volume. So that's like a rigid container. Like if this was filled with gas, right? It's pretty rigid. Okay. What happens? We heat it up. What happens to pressure? Goes up. Particles gain kinetic energy, start moving with faster velocities. By the way, you're going to be responsible for figuring out the velocity of particles, like how much kinetic energy they have and how fast they're moving. And it changes depending on what gas it is. Think about someone who's really like a really big person, like a professional football player, 6'7", 300 pounds, or someone my size. It's going to take a lot more energy to get the big person moving. Does that make sense?
Mm-hmm.
A lot more horsepower. Okay. T and V.
Up.
Yep. That's like a hot air balloon.
Down.
Yeah, but now you gotta,
Curve,
yep,
whatever.
okay. Alright, oh, there's another way to do this graph, actually.
What one?
This one.
That's a 1 over V.
Yep.
That would work for, or is that just add?
What's this graph look like?
Same thing.
Yeah.
No,
How can it?
opposite, the whoop, upwards.
Yeah, it's direct, actually.
Oh. That's close. Sit up.
Okay, this is Boyle's law, Charles' law, Lusak's law, and then there's another law called Avogadro's law, or Avogadro's law. And you're gonna learn a new gas. What are you laughing at?
He said Avogadro sucks.
Cool. What's the last thing? You guys remember? All right, we'll talk tomorrow. We'll learn the ideal gas equation. It's a big day tomorrow.
What were we supposed to laugh at?
Tomorrow.
So nothing was funny.
Tomorrow.